Thank you very much for joining the fifth FLEXIndustries webinar. Today we're here with Vasilis Tatsis, which is going to be the speaker for the webinar. So, of course, as always, we are recording the meeting, so it will be available in the next few days on our social media channels. And of course, if you have any questions throughout the meeting, please write them in the chat and we will answer them at the end. Okay, I'll leave the floor to Nicola for the introduction and then we'll start.
Okay, thank you, Martina, and good morning, everyone. So I'm Nicola Santoni, the coordinator of FLEXIndustries, and today I'm very pleased to introduce today's speaker, Vasilis Tatsis from CERT ITI, who, in addition to being one of the project's work package leaders, has an extensive experience in, among other things, obviously, writing optimization algorithms and machine learning. So without further ado, let's begin this webinar. So please, Vasilis, the floor is yours.
Thank you, Nicola and Martina. Welcome all. So in today's webinar, we will discuss know if you can see my screen.
Yes, we can see it. Yeah, perfect.
It's for screen, right?
Yes, thank you.
Okay, perfect. So today's webinar is focused on discussing some of the achievements and the results that we achieved through the FLEXIndustries project regarding the optimization forecasting provided solutions that we have offered for in order to achieve the industrial flexibility as desired. So we will start analyzing in this webinar. We will start with all the provided solutions that we proposed for this project, and then for each one of them, we will see also some results from some of the pilots, and we will have some time to discuss also some things if anyone wants to ask something. So as I mentioned, we have this. Here is the roadmap of the provided solutions for this project. We offered some solutions, some optimization solutions regarding single and multi-objective optimization problems. We will discuss about this later. Furthermore, we have offered some machine learning solutions corresponding to forecasting, classification, neural networks, some LCE and LCC tools, and also some rule-based methods in order to analyze some patterns in some of the pilots in order to mitigate some penalties. We will discuss about each one of them briefly in the next slides. If we see it from the FLEXIndustries project, this is the pipeline, how actually we structured all the solutions starting from the pilot's data to the actual solutions, as we mentioned before. And as you can see, only in the first one, in the optimization solutions, we need the input for them from the forecasts solutions that we provided. Just to keep in mind only this. The other one are independent solutions. So starting with the first machine learning algorithm and the provided solution regarding the electricity and gas price forecasting. In this solution, we focused because we had as I mentioned, the pilots, they were in these 6 countries. So we wanted to forecast the price, the electricity price, prices for these 6 countries. And to do this, we start analyzing very many literature algorithms regarding what is the state of the art of the algorithms regarding the forecasting methods. And for this purpose, we used also univariate and multivariate algorithms. And as we can see, we used different various of predictions and methods in order to achieve the results that we will see in the coming slides. Also, we because hyperparameter tuning is a crucial issue in all of machine learning and optimization algorithms, and for this reason and for this provided solution, we use the hyperparameter tuning implementation, not a sophisticated one, but through random grid search, actually, in order to find the best parameters for the forecasted algorithms. Here, in the next slide, we have these are the day-ahead prices from for a big horizon. I think these are for 2 years for the 5 different countries. Here, you see that in some countries, for example, in Bulgaria and Greece, we have more spikes compared to the other countries, and this makes the forecast a bit more tricky. And this happened because of various factors and market conditions. Also, to help with the price forecasting, we used here we have these are, we can say, like a heat map where we can identify where the grid needed the most energy and consumed the most energy from these countries, and this could help to have a more accurate price forecasting, except of reading only the time series of the previous days and the historical data. Also, we analyzed, we had the future importance regarding the random forest. We used many algorithms, machine learning algorithms for the price forecasting, but random forest was proved to be the best one, along with some other algorithms as well. Here, as we can see, we analyzed the features that they are more relevant and can influence more the algorithm and the corresponding forecast as well. And these details are more technical, but not very familiar to the end user. But regarding the performance that we achieved for each of the countries, here we have some metrics that can measure the accuracy of the predictions. The smaller the value, the better. As you can see, as we saw also before from the graphs, for Bulgaria and Greece, we had good results, but these are the worst between the countries because of the spikes, as you saw in the previous images. But again, we achieved to have really good price forecasting accuracy. Here we have some visualization of the actual with the blue line and the predicted with the, I think, yellow or green, whatever this color it is. And the predictions were really accurate, at least for these are for a specific day, as you can see here in the legend. But when we change to some other dates, again, we achieved to have really good forecasting results, except some rare conditions. For example, like in Poland, where you can see that here we have a big dip, a big peak here from the opposite side, where the predictions were really close, but not so accurate. But this, in the long term, doesn't play a big role, because we used this price forecasting along with the other forecasting solutions that we will analyze in the upcoming slides, in order to have, as I said in the first slides, to achieve the flexibility through the optimization problems, through the defined optimization problems for each one of the values. Here we have also again some other examples to see also, except of the metrics, to see how the price forecasting actually is compared to the real, to the actual prices. Again, as I said before regarding Bulgaria, here we have some not so accurate forecastings due to the spikes that you saw in the first graph, but again we achieved some really good results even for these rare conditions for Bulgaria and Greece in some cases. Also, for this project, we wanted to forecast the natural gas, and a similar approach was followed again for the natural gas, with some different algorithms and parameterization and some other tricks that have been applied for the natural gas. Here we use the univariate algorithm, not a multivariate as we saw in the price forecasting, in the electricity price forecasting. If we analyze the gas distribution, price distribution by month from 2018 to 2025, we can see that most of the values are not they're not having extreme values, except of these cases here between I think 2021 and 2023. We had also we have implemented also some correlations, autocorrelations and partial correlation regarding the natural gas, and these also correlations help us to achieve more accurate results as well. Again, here we can see an example of the actual values and the predictions for the natural gas price. And as you can see, the deviations are not significant. There are some deviations because natural gas is more tricky to some factors to predict it, but again, for the purpose of this project, it was enough to achieve the results that we wanted to achieve through the flexibility solution. And now, jumping to another machine learning forecasting solution, which is the demand forecasting. For the demand forecasting, we have implemented two different algorithms. Where the first algorithm is based on some linear regression models, where we are creating the profiles for each day of the week, trying to analyze all the seasonalities and cluster also the months and the day of the weeks in order to have more accurate results. And this is the analytical way of producing the forecast with and the simpler solution, because we have many linear models that needs to be trained per horizon and per cluster. And in combination, along with this forecast solution, we have also implemented another more sophisticated solution using LSTM networks. The LSTM networks are they belong in the deep learning algorithms. They're called long short-term memory networks, and because these networks are trying to learn all the patterns that the previous method, the linear models are trying to let through all the analysis that I briefly discussed, mentioned before. These networks are trying to let all these patterns from the time series, and for this reason, the parameters of these networks needs to be near the optimal values, and thus we implemented and we created a hyperparameter optimization method that uses in the head of this hyperparameter tuning method a differential evolution algorithm sits. This algorithm is a metaheuristic algorithm from the optimization artillery. And all of these, the combination of the novel parameter tuning algorithm along with the LSTM provided the forecasted values that we want also for the flexibility. And we have some results, some comparisons between these two approaches. Both of them, they had really good results. Also, this approach where all the patterns and everything, the seasonality, is not analyzed from the end user, but we let the model learn all the underlying patterns of the time series data. Here, we have some results, let's say for pilot 1, where we have also for the price forecasting and for the demand forecasting, the predicted horizon for this project was the day ahead, so 24 steps ahead for the one prediction for every hour of the day. And here we can see that along again with some metrics, right, like the normalized MC, we achieved some really good results, even for some of the most demanding forecasting pilots, as we will see in the upcoming slides. I don't want to bother you with many details regarding all of these graphs and the results, but if you want, we can discuss later in the questions, in the time that we have some questions. But again, I want to show you some graphical representation of the actual values and the predicted values. This graphical representation is from the deep learning with STM and hyperparameter tuning approach. And again, we have the metrics. Here, the predictions were okay, not so good with the deep learning approach. They were better with the linear regression models. But in some other pilots, we had also some better results with the deep learning models. Here, for the pilot, we changed to pilot 2. We analyzed again with the linear regression models all the patterns, as I mentioned before, regarding the days of the week and regarding some other seasonality patterns and the months, as we discussed. We did specialized clustering of all of this, and we trained different linear regression models. And the results, again, for two different rooms, let's say for easiness and the total one, are here. We have the results with the clustering and without the clustering. And as you can see, with the clustering, the results are obviously better and really accurate also for all the predicted horizons that we want. And here, if we compare it with the LSTM models, the predictions were really good as well with the LSTM models. Even in these cases where the pattern slowly changes, as you can see, the models were capable of identifying these patterns and continue with accurate predictions. Here again, we have some metrics that indicate the prediction accuracy. The smaller the values, this is the better for all of them. And for this pilot, we had also to predict various different aspects like energy, steam, water, because the load forecasting was a combination of many time series from many pilots from this project. And for this reason, again, we use the same algorithms as I mentioned before, the linear regression models and the deep learning models. The results are similar. We had a really good accuracy. Here, again, we see the predictions for the deep learning model, but again, for the linear regression model, the results are similar. And changing to another pilot, we can see again that for all the targeted aspects, the results were really accurate. Now, moving to the another machine learning algorithm regarding the photovoltaic forecast, the PV. Here we have a different approach, because to predict the production of a photovoltaic panel, the story is a bit different, because you need also weather data, except of the time series data, as we did with the previous results, except the price forecasting. And to do this, we used an external weather service where we stored all the weather data. As you can see here, we chose these being 7 different parameters for the weather in order to have accurate results, and we stored them in an internal storage server in the FLEXIndustries project. And using this weather data along with the time series that we had from the PVs, we had again really accurate predictions, because most of the predictions they can be significantly influenced from the cloud coverage. So the weather forecast plays a crucial role in this solution. And all of these aspects that we saw, the provided solutions, the price forecasting, the PV forecasting, and the demand forecasting, as we will see in the coming slides, they will be used to provide the flexibility through the optimization solution. But before we jump to the optimization solutions, we had also we have implemented also an anomaly detection algorithm in order to classify the anomalies for some of the pilots that we had this need. The anomaly detection algorithms that we used here, we had 2 different family of algorithms, because to predict accurate an anomaly, except of the data, the historical data that you want also the data to have labels with the faults that occur during the period that we examine, in order to have more accurate, not only predictions of the fault itself, but also to have a label what fault probably will be in the upcoming hours, or the predicted horizon that we want every time for the anomaly detection. So for this reason, we have the supervised anomaly detection algorithms, where we can use the labels, the faults that we have from the historical data in order to connect the faults with the predicted anomalies. And we have the unsupervised anomaly detection algorithm, where we can identify and predict an anomaly in the future, but without knowing what anomaly is this, because we don't have the labels, as I said. Again, the anomaly detection is a tricky procedure because most of the anomalies, as we saw also from other, from our experience from other projects, occur within some minutes before the actual fault happen. And to predict it prior to this fault, for example, before 2, 3, or 5 hours is not so easy. But in this project, we achieved some really good results, and we were be able to predict the anomalies for one of the pilots within the time that the pilot wanted. Actually, it was 3 hours before. And to do this, we used various ensemble optimization models because one machine learning algorithm was not enough to catch these anomalies early. And here we have some more details regarding how we pre-process the data in order to remove some of the outliers, to identify the anomalies, to create the supervised data set for the supervised machine learning algorithms, because for this test pilot, we had also the labels. So at least for some of the cases, also we used, as you will see, and I will try to explain it more easily in the upcoming slides, except the machine learning algorithms like the isolation forest, random forest, and some variations of these algorithms. We had also the ensemble anomaly algorithm, where we merged the output of the classifier of all of the classifiers using an ensemble model in order to have more accurate results. But in order to maximize the prediction from the ensemble model, we used also an optimization technique, an optimization algorithm to optimize the weights for the ensemble model, as well as the anomaly score, the threshold, where we consider an anomaly as an anomaly. And I'll try to explain it more easily in some of the following graphs. For example, here you can see the results with the isolation forest, random forest, one different parameterization, and all of the separate machine learning algorithms for the corresponding pilot. Again, here we have some metrics. These are all metrics from the hits of the classifier, and all together, when we have the ensemble model, I think here is the most interesting part for this webinar. As you can see here with the red line, the anomaly, the pattern changes and changes quickly. And here the anomaly occurred during the end of this time series. And in order to predict this anomaly within the time that the pilot wanted, actually it was around 3 hours, we used the last one. This is the weighted mean and the threshold optimization, the ensemble model, with the optimization of all the internal weights and the threshold, in order to identify early that this this value here is probably an anomaly, even if it's similar to the previous historical values, as you can see, we will be able to predict the anomaly within the 3 hours time window, as I said. But without this, with the ensemble model with optimization, if we use only one isolation forest or random forest, the results were for some of the cases good, but not so good as with the ensemble model with the optimization. And to give you a better idea, because this is also a complex topic, the output of the anomaly detection algorithms belongs to the range of 0 to 1, and we try to depending regarding of the value, to classify this value as a normal one or an anomaly observation. And this where the threshold comes. That's why we want to optimize also this threshold in order to identify if, for example, this value is more than 0.6, if this is considered an anomaly or not. This is a big picture behind the anomaly detection algorithm. And again, along with the previous tools that we saw, we had also some machine learning neural networks in order to identify some correlations and more specifically to identify the most significant parameters of an ORC. The ORC is a machine that produces energy through it's a hardware that produces energy through waste heat, and we have installed these systems also within the FLEXIndustries project. And again, here we see some of the internal parameters of some of these machines. For example, the ORC that we analyzed here, and we tried to identify the most significant parameters, the most significant internal parameters that can affect the actual energy production of the ORC. And we wanted to do this in order to have a more accurate prediction of the production from the ORC, because as you saw before in the previous slides, we had the demand forecasting where we used only the time series of the historical data. And when these machines will be installed and we have enough data to train, to have accurate results with identifying the most significant parameters, then we can also feed these parameters into the demand forecasting in using a multivariate model in order to have more accurate results than having only the time series that we have right now. This is, again, the big picture why we use this correlation analysis. And to do this, we have implemented different algorithms. Again, I will not mention more details about this. The outcome is that we will be able to cluster the internal parameters as medium, high, and very high correlation, meaning that these parameters can significantly change the output of the ORC. That's why we want to pay attention probably to these values when we want to have more accurate forecasted results for the ORC. And to do this, we use various machine learning algorithms and hypothesis-based algorithms. With the red in both of these graphs, we can see that these variables, these parameters, they have no contribution. This one, for example, while these two have the most contribution. And now, moving to the one of the final provided solutions where we merge almost all the solutions, all the algorithms that you saw before. Here we have the single optimization algorithm we have for this project because the requirements were different for some of the pilots. We have the single objective where I will analyze more in detail what it means, and the multi-objective optimization. The single objective it refers to minimizing only one objective, meaning that here we want to minimize the cost, let's say, of a factory. To do this, we created the optimization problem where we have the load forecasting. Here we have the generation forecasting, as we saw, for the energy source, either if, for example, the ORC, the other energy sources from the factories. And we have, again, the price forecasting from the price forecasting module. And we have the demand forecasting, as you can see here in the bottom of the slide. And in order to provide the flexibility, because this optimization algorithm provides the day ahead schedule for a factory in order to follow, think about it like some action, what to do for the 24 hours ahead, depending on the optimization problem itself, in order to achieve, for example, to minimize your cost, to consume less energy from the grid, because where you want to consume electricity from the grid, you need to pay the current price. But in this case, we have also the energy source where we can save the produced energy in an energy storage system, like a battery-based system, for example. And then, depending on the prices of the market, we can and of course the demand, we can find the optimal usage of the energy resources and the consuming from the grid the energy in order to cover a specific demand. And with this way, we provide the flexibility for the day ahead actions for each for the corresponding pilot. Again, here we see the general case of the energy optimization algorithm. I explained it quickly before. We have the energy generator, the base system, the grid, and actually we choose all of these energies to self-consume or to buy and sell the energy to the grid. To sell the energy to the grid, for the moment, most of the pilots they are not supporting this option, but because there are some regulations that they need to solve in the upcoming months. But when they will be able to sell the energy, they will have also some profit by selling the energy to the grid when the demand is high in the grid itself, and we don't want to consume this excess of energy in the factory. Here we have some results for the day ahead schedules. For example, here we see that in order to cover a specific demand, we need to, for example, discharge the battery, or to use this amount of energy from the ORC, this amount of energy from the other system, and so on, in order to cover the demand and minimize the cost or maximize the profit of the factory. It's the same meaning. Again, from another pilot, the results are similar, the same story, where we have the battery and the forecast and the demand as well. And now, moving to the more complicated optimization solution that we provided for the flexibility. in this solution, we wanted, except of minimizing the cost, to minimize also the CO2 emissions, because here in some of the pilots, we have not only one energy source, but we have different energy sources, as you can see, the grid, the battery, the PV, and some other specialized machines. And the results that we achieved even for this complicated situation, they were really accurate for some of the cases. Here with the blue line, you can see the demand that we want to cover, and and here you can see from which energy source we receive this energy in order to cover the demand. And these graphs, for example, above the demand are the excess energy that we need to sell it or to store it in the battery. For some of the pilots, we had some other problems to solve regarding the mitigation of some penalties that they pay because they purchase more energy than the energy that they want, and usually this action comes along with a penalty because you consume more energy than the energy that you forecast that you want to consume. For this test case, we had again two different solutions. This one that I will show you, that eventually we developed that, but we didn't implement it because it was the most complicated solution. And some of the pilots wanted the simpler solution that I will show you in the upcoming slides. The idea here is to avoid these penalties because you don't want to consume more energy than the energy that you bought, because to consume more energy from the energy that you have already bought, you need to pay the penalty for this, and we want to keep it below this threshold. For example, this is a graphical representation of what we want to achieve with this. And to do this, you need, for example, to turn off some things, or to have a schedule which machine and for how long to turn off during the operation, following again some rules from the factory regarding this, how much time you can turn and which machine is more preferable to turn off during this period. And again, as I said, because this is again an optimization problem, we used a novel online parameter tuning method that have been created also for this project. The previous method that used to tune the LSTM models used also here based on some previous work that have been done in this area. And the output was something like this. For example, you need to, in order to achieve the consumption that you want, this is the fixed consumption, you need to close, for example, these machines for this amount of time. But because this is a fixed solution, the pilot wanted to have more solutions, not only one, and in order for them to decide which machine to turn off. So for this reason, we changed to another the rule-based solution that I mentioned before. And here we don't use a sophisticated heuristic optimization algorithm. We just use some rule-based conditions, trying to identify which machine to turn off and for how long. And this approach provided us with the results that we wanted for this pilot. So we didn't proceed with the previous one, the more complicated solution. Last, we have two different tools. The grid monetization tool and the LCA, LCC tool that you will see in the upcoming slides. Regarding the grid monetization, the idea is that we can shift the some of the procedure within the factory regarding the energy, the energy prices from the grid, and in order to shift this these energy consuming, let's say, procedures from some not ideal time windows in the day ahead planning, and by shifting these procedures, we can achieve this the grid monetization. And with shifting this energy demand, as I said again, from high prices, we reduce imbalance cost and have also some other advantages for the pilot. To do this, for example, this approach have been implemented for the Bulgarian pilot that we had, and we used again some information with the heat map and the price forecasting, and we analyzed, as you can see here, here we can see the actual and the forecast values of the consumption of the factory, and as you can see, the results for each month. These are the average consumption for all the factory for 1 month and for the whole year in order to implement this grid monetization. We used also some additional information like the average deficit price, the average actual consumption, deviation, and all of these internal aspects for this solution in order to achieve the desired results. And here, as you saw, we have this the shifting of the demand, as I mentioned, in better times for the corresponding pilot, and we achieved also some really good results even for this test case. And final, regarding the LCA and LCC tool, we created two independent tools where we wanted to create a user-friendly tool for calculating the CO2 emissions and to increase the stakeholder awareness and to calculate all the life cycle assessment evaluations for this for all of the pilots. And for this reason, I don't want again to bother you with all the details. These are separate tools along with the tools that I mentioned before. All of these tools, they have a unique graphical user interface where the end user can change many of the parameters, can see the results in real time, and can interact with the system. And regarding the measure the performance of these algorithms, again, here we have some slides what KPIs we use and we want to use in order to measure, for example, what flexibility we provide with optimization solutions. And a way is to measure the cost reduction rate from the optimization without the optimization solution with forecasting algorithms, because this, if you recall, they are not providing the flexibility by themselves, but through the optimization algorithm. That's why we have this KPI here. But to measure also the performance of the forecasting and the anomaly detection algorithms, we have specialized metrics like the RMC and all of the other metrics that you saw during the presentation of the results. And here we have some more, again, KPIs for the forecasting regarding the Mathis correlation coefficient, but all of these are more technical details if someone wants to ask something. I know that this webinar probably was, it had a lot of details, but this project had a lot of implementations, a lot of test cases, and I hope you understood the presentation. And if you have any questions or anything more abstract or more in detail, we can discuss it in the minutes that we have. Thank you. Thank you from my side.
Thank you, Vasilis, for your presentation. I don't see any questions at the moment, but we'll just wait maybe a minute. So if anyone has any questions, you can ask now, and after that we can close the webinar. Okay, I don't see any questions for now, so I think we can start closing the meeting. I remind you that, of course, we have recorded the meeting, so if anyone wants to watch it again, you can. In the next few days, we will upload the recording on our website. So thank you all again. Thank you to Vasilis for the presentation of today, and stay tuned for the next webinar for the project. Thank you.
Thank
Bye,
you.
everybody.